So let's talk about covariance. Covariance is another number that we can calculate from a pair of random variables. Okay, so in that sense, it's sort of in the same category as expected value and variance that we calculate a number that we calculate from the PMF of a single random variable. Covariance is something we calculate from two random variables. And it tells us how the random variables are related. Okay. If it's positive, they have a positive relationship, meaning that when one is high, the other is likely to be high. When one is low, the other is likely to be low. When covariance is negative, it means they have a negative relationship, meaning that a high value of one tends to go with a low value of another. Okay, so let's see how that works by looking at the definition of covariance. So the covariance of x and y is the expectation of x minus the expected value of x, my x bar there, times y minus the expected value of y, okay, the expectation of that whole thing. So, it's kind of got that style that we associate with a variance. We're subtracting the expected value of a random variable from its realized value. But there's a couple things that are different. Okay, so let's kind of observe some things here. Okay, so first thing I want to observe here is you're looking at difference between the random variable and its expected value. Okay, so we've got x minus x bar, y minus y bar. So the difference between what x actually works out to be and the expected value. Again, sort of reminding ourselves it's the difference between a random variable and a number. Okay, it's a special number, but it is really just a number. Okay, what's different here is we are not squaring the differences. Right, when we define variance as the expectation of the squared difference between the random value and its mean, we were doing that because we didn't want the sign of the difference to affect things. When we're calculating covariance, we do care about the sign. Okay, we care whether x is greater than x bar and y is greater than y bar. That's a really important thing for the covariance. So we're just taking the product of the simple differences, or you might even say the signed distances there. And we're taking the product. Okay, so let's think about what that means. Okay, when x works out so that it is greater than its expected value and y is also greater than its expected value. So we might think of this as x is high relative to its typical value and y is high relative to its typical value. Well, we have a positive here and a positive there, and a positive times a positive gives us a positive. Okay, so the product is positive. And when x is low relative to its expected value, okay, so for whatever scale x is on, when x comes out to be on the low side of its possible values, and y does too. Okay, so we've got two negatives here. In that case, also the product is positive. Okay, so same story, product is also positive here. And what this is doing is the more probability that is assigned to these cases where X and Y are both high relative to their means or low relative to their means. If that's where most of the probability ends up, this is going to push the expected value toward a positive value, okay? And when looking at the other case, when X is relatively high and Y is supposed to be a Y there, Y is looking like an X. That's better. Y is less than Y bar. Okay, so when we're in the situation where X is relatively high and Y is relatively low, or X is relatively low and Y is relatively high, then we have a negative product. Okay, this thing whose expected value we're taking, this whole product here, is going to be negative. And the more probability we're assigning to that is going to, let's make that green, push the expected value toward the negative. Okay. Okay. So this definition of the covariance, if we pick it apart and see how it actually works, it helps us understand why this is giving us a measure that's letting us know overall, do X and Y tend to move together so that when one is high, the other is high, and when one is low, the other is low, or do they tend to move in opposite directions so that when one is high relative to its mean, the other one is low, and then vice versa. So we'll see in the next lesson that just like with variance, the definition is good for understanding the logic, but we'll have a formula that we use much more often that's better for calculations and derivations. But before we get there, the formula is not terrible. So let's use this definition to calculate the covariance of X and Y from last lesson's school board, city council examples. Okay, so let's go to a new page for that. Okay, and let's remind ourselves what we had going there. Just write the crosstabs here. X took values 1 and 4, Y took values 1 and 2. The joint probability of 1 and 1 was 0.365. The probability that X equals 1 and Y equals 2, 185, 0.185 here, and 0.265. The marginals were 0.55 and 0.45, both cases, for X as well as Y. And what's the other thing I want to remember from, oh, I want to remember their expected values, right? Because I'm going to need those. Okay, so the expected value of X we found, and one of those many lessons last time was 2.35, and the expected value of Y was 1.45. Okay, so that's all kind of from last time. Let's kind of corral it over here. And now, what we want to find the covariance of X and Y. And so that is the expected value, just reminding ourselves the definition that we had just a minute ago, the expectation of X minus X bar, Y minus Y bar. Okay, fine. In this particular case, it's the expected value of X minus 2.35, right? That's my X bar here, and Y minus 1.45 Y bar there. Okay, so the easiest thing for me to do is to take this function now of the two random variables. Okay, so what we're taking expected value of here is, of course, a random variable. We wouldn't be taking expected value if it wasn't. It's a random variable whose value depends on the values of both x and y. So let's write down the PMF of that. And as I kind of like to do when I'm doing this systematically, let's call this thing here z. Okay, just gonna give it its own name so I'm not distracted by the fact that that it's coming from x and y in this fancy way. Okay, so the PMF of z comes from the PMF of x and y. So just reminding ourselves here that this is maybe more redundancy than I need, but let's just be clear about every step. So when x is 1 and y is 1, that happens with probability 0.365. And what that means is that z is x is 1, so x minus 2.35, that's the expected value of x, multiplied by y, which is also 1 here. And we are subtracting y's expected value, 0.145, and that equals 0.06075. I've got too many z's floating around here. It's too much. I'm going to just erase this guy. When x is 1 and y is 2, that happens with probability 0.185. And so z, x is still 1. We've got 1 minus the expected value of x. Now y is 2, so we've got 2 minus the expected value of y, and that comes out to be negative 0.7425. When x is 4 and y is 1, it also happens with probability 0.185. So now x is 4, subtracting off expected value of x, multiplying that by y equals 1 in this row, subtracting off the expected value of y, that also equals negative 0.7425. Yes, we just got the same number in 2 rows. Don't get too excited about that. It's happening because this is a super simple random variable with just 2 values, and the cases happen to have the same probability assigned to them. It's generally not true that these will always be the same. The final pair of values that x and y can take is x can be 4 and y can be 2. That happens with probability 0.265. Put that there. Plug in my values of x and y into my formula for z. 4 minus 0.235. 2 minus 145. That equals 0.9075. Okay, so this is the PMF of this intermediate variable z that I'm using to calculate covariance. This is the thing whose expected value covariance is. So let's just calculate that expected value of z right here so I'm going to calculate the expected value of z using these, okay, because these are the probabilities of z. Maybe I'll write this in ink here. These probabilities are the probabilities of z, and these are the values of z. And so the expected value here with probability 0.365, z takes the value 0.6075. Okay, so this probability, that value, plus probability 0.185. Z takes the value 0.25, and the same again for the next row, also with probability 0.185. Get another 0.7425. Coming around here, continuing the expected value here with probability 0.265. Z takes the value 9.075, and I punch that all out. on my calculator, and what do I get? I get 0.1875, and yes, this is the covariance of X and Y. Okay. I got the covariance by finding the expected value of the product of X minus 2.35 and Y minus 1.45. I picked those numbers, 2.35 and 1.45, because they are the expected values of X and Y. And the number that I get, the expectation of this product here, is my covariance. In this case, it's a positive number, and that makes sense. Going back to the example that these numbers came from, when the electoral environment was such that X was likely to be high, because it was that anti-incumbent sentiment that was driving it, that electoral environment had the same effect on Y. So this common latent variable, we might call it, that's affecting both X and Y is having the same effect on both of them. It's pushing them both either in the positive direction, or if that anti-incumbent sentiment is not present, it's pushing them in the negative direction. So we should expect that X and Y have a positive covariance. They do, and that's what we have so far. So I have a few more things to say about covariance, but we'll go to a new lesson for that one.